Good morning, students. In this lecture first of mechanics, we'll discuss rigid body dynamics. So before studying the dynamics of the rigid body or the motion of the rigid body, we will first discuss that what is the meaning of rigid body. So ideally, the rigid body is the body. I'm discussing the ideal case. Ideally, the rigid body is the body in which the distance between its particles remains constant or remains same. Or you can say that the distance between the particles inside the rigid body doesn't change even when we apply some external force on the body. So, even on applying external force on any body, if the distance between any two particles of the body, it doesn't change, then that body is said to be a rigid body. And in other words, you can say that if a body on applying force on it retains its shape, means if the shape of the body doesn't change even under the effect of the force, then that body is said to be a rigid body. In case of rotational motion, we can take torque instead of force. So force in the translatory motion and torque in the rotational motion. So under the effect of both of these, if any body, it doesn't change its shape, then that body is said to be a rigid body. But actually, in reality, there is no rigid body. There is no rigid body in real sense, or you can say that there is no ideal rigid body. Why? Because in real world, on applying force or torque on any body or on any solid, the shape of that solid or the distance between any 2 points inside that solid, it will change even though that change will be very small. That we can ignore that change, means we can take that body approximately a rigid body, but in real sense, no body in real sense is a rigid body. Why? Because there is always some deformation in that body. There is always some deformation in the shape of that body when that body, it is under the effect of some external force. So you can take the example of the bridge. Bridge is a rigid body. We take bridge as a rigid body. So in ideal case, there must not be any change in the shape of the bridge under the effect of the applied force. So when one person will walk on the bridge, there will be no change in its shape. But if heavy loaded trucks, they will pass through the bridge, then there will be some change, there will be some deformation in the shape of the bridge, even though that deformation is so small that we are not able to see it. So these deformations, they can be ignored, but they are actually there. So in real sense, no body is an ideal rigid body. So what will be the practical definition of rigid body? So practically, a rigid body is a body in which its constituent particles, they are nearly at a fixed distance. Approximately, they are at a fixed distance from each other, and in case of a practical rigid body, all these particles, they will execute small oscillatory motion about their mean position. So practically a rigid body is a body in which all of its particles, they are approximately at a fixed distance from each other, and at the same time they are executing small oscillatory motion about their mean position under the effect of the force acting on them. And why we are taking that rigid body? It consists of particles, because every body, it is made up of atoms. And here we are taking those atoms as particles. So that is why we are considering that a rigid body, it has its constituent particles. So practically, for practical purposes, we approximately take all solids as the rigid bodies. So now we'll discuss the motion of the rigid body, and the shape of the rigid body, it can be any. It can be circular, it can be spherical, it can be linear, and it can be any arbitrary shape. So now we'll discuss the dynamics of the rigid body, or you can say that a motion of the rigid body. So a rigid body, it may undergo straight line motion, that is known as pure translatory motion. Second is, if you fix a point inside that rigid body, and that rigid body, it can rotate about that fixed point. So second type of motion of rigid body is rotation about a fixed point inside the body or outside the body. And third one is, if you fix one line inside the body, which is known as axis, and then about that line, you rotate that body. That is known as rotational motion or rotation of a rigid body about a fixed axis, which is passing through the body, or it can lie outside the body. And fourth one is general motion of a rigid body. We'll study all these types of motions of a rigid body one by one in this chapter. So this I have already told you, that a rigid body, it may undergo translational motion. It may undergo rotational motion about any point that is fixed. It may undergo rotational motion about any axis which is passing through the body. Or it may undergo a revolution around an axis which is lying outside the body. Suppose we have any rigid body. It can rotate about a fixed point lying inside the body. It can show translatory motion. It can show, or it may undergo rotation about an axis which is passing through the rigid body, and it may also undergo revolution about an axis which is lying outside the body. So it will rotate in this way about this. So first we'll discuss translatory motion. Translatory motion of a rigid body. So when a rigid body, it moves in such a way that with the motion of the rigid body, all of its particles which are inside the body, which the rigid body is composed of, they also move in a straight line in parallel to one another with the same velocity, with the same acceleration, and the displacement of one particle with respect to another particle means their relative displacement is zero, means their distance, even during the motion, the distance between those particles remains constant, means their relative displacement is zero. Then this type of motion of a rigid body is known as translatory motion. So for this, suppose this is any rigid body. This rigid body, it is moving in this direction. So after some time, this body, it has reached at this point. Shape of the body will remain same. Now here this body, it consists of particles or atoms, large number of particles. I am considering few of them. So when this rigid body will move from this point to this point in a straight line, what will happen? All of its particles will also move. And they will move in such a way that their distance from one another, that will not change, that will remain same. Means their relative displacement is 0. And they are moving with the same velocity. If the velocity is same, then their displacement will also be same. So the displacement of every particle is same. If this particle, it has covered 7 meters, then this particle, some jth particle, it will also cover 7 meters. So displacement of ith particle and the displacement of jth particle inside the rigid body during its translatory motion will be same. So upon differentiating with respect to time, what you will get? dsi by dt, it is equal to dsj by dt. And what is displacement upon time? It is velocity. So this implies the velocity of ith particle, it is same as the velocity of jth particle. So that is why I have already said in the definition that all of the particles, they are moving parallel to each other and with the same velocity. And if the velocity is same, then again after differentiating with respect to time, what you will get? That acceleration is also same. Because velocity upon time is acceleration. So acceleration of ith particle inside the rigid body, it is same as that of the acceleration of jth particle of the rigid body when the rigid body is under the translatory motion. So in case of translatory motion, a rigid body, it moves in a way that all of its particles, they move in a straight line, then they move parallel to one another, then they move with the same velocity and same acceleration. That is why their distance at the initial position and the distance between them at the final position remains the same. Means their relative displacement is 0. So this is all about translatory motion. Now we have discussed lab frame and center of mass frame in our previous semester. So now we'll view this translatory motion of the rigid body from the lab frame. And this rigid body, it will also have its center of mass on any point inside the body. So the velocity of as all the particles, as I have said just before, that all the particles of the rigid body during its translatory motion, they move with the same velocity. Therefore, the center of mass of the rigid body, it will also move with the same velocity as the velocity of its all particles. So the velocity of center of mass of the rigid body, it will be same as the velocity of its particles in lab frame. But when you will view this translatory motion from the center of mass frame, and you might remember that in center of mass frame, the origin of the coordinate system lies at the center of mass of the body. So if origin of the coordinate system lies at the center of mass, and with respect to center of mass, all the other particles, they have same velocity as that of the center of mass. So if the center of mass is moving with the velocity v, and all the other particles inside the rigid body, they are also moving with the velocity v, Then to center of mass, what will seem? That all the particles inside the rigid body, they are at rest. Means from the center of mass frame, when you will view from the center of mass of the rigid body in the center of mass frame, what will happen? What will you observe? Observe that velocity of the rigid body will be 0. Means the rigid body is at rest in center of mass frame. Why? Because the velocity of the center of mass and the velocity of all the particles, that is same. So from the center of mass, it will be observed that all the particles, they are at rest. Means the rigid body is at rest. So that is why rigid body is at rest in center of mass frame. But from lab frame, actually it is moving. Then there is another term which will be used by us later in this chapter, that is torque. What is torque? During the linear motion or the translatory motion, we use the term force. But during the rotational motion, because of that force, the body, it will undergo translatory motion, linear motion. But which force causes the body to exhibit rotational motion? It is the torque. So actually this torque, which is rotated by tau, it is the rotational equivalent of the linear force. The force which we take in translatory motion, its rotational equivalent is torque. So what is the torque? It is actually the measure of that force which causes any object to rotate. Which causes any object to rotate about an axis. So this is torque, and few more terms which we'll use later in this chapter. They are center of mass and center of gravity. So now we'll discuss that what is center of mass, what is center of gravity, and what is the difference between the two. Center of mass, as you have already studied its definition in our previous chapter, what was it in case of central forces? Center of mass is the point where whole mass of the body is supposed to be concentrated. What is the meaning of this? So actually, center of mass is that point at which the distribution of mass is equal in all the directions. So now I'll make you understand that what is the meaning of this definition. So let us take the example of a rod. First of all, take the example of this rod. Suppose you have this rod shown by black pen. That is rod. And everything in this universe, it is made up of atoms. Elementary particles. We are considering atom as an elementary particle. And we know that atom, it further consists of electrons, protons, neutrons. Then further protons and neutrons, they are made up of quarks. But we are just considering that, our study, that this rod, it is made up of atoms. And we are considering those atoms as particles. So these circles, actually these are the particles which this rod is made up of. And why I have taken this point as center of mass? When you will count these particles, they are 20. Means this rod, it is made up of, I am just supposing this, that this rod, it is made up of these 20 particles. Then what will be the center of mass of the rod? Center of mass of this rod will be that point from which on this side we have same number of particles and on this side we have same number of particles. Means from that point on this side there is same mass of the rod and on this side there is same mass of the rod. So from this point there are 10 particles lie on this side and 10 particles lie on this side. Means we can balance the rod about this point. Because about this point, the distribution of mass is equal on both sides. So that is what this definition indicates, that it is the point at which distribution of mass is equal in all the directions. So then take a circular disc. Take the example of a circular disc. This is the center of mass of the circular disc. So this is that point from which on this side, on this side, on this side, on this side, on all the sides, the number of particles are same, or the distribution of mass is same in all these directions. So that is why this point is center of mass. Suppose this is circular disc, this is circular disc. Then this point will be the center of mass of this circular disc. Why? Because there will be equal distribution of mass in all the directions, and if you have to balance this circular disc over this pen, then by keeping this whole circular disc resting on this point over the pen, this circular disc can be balanced. So that is the center of mass of the circular disc. Then take the example of the sphere. For sphere, imagine a ball. Ball is a spherical body. And in case of a spherical body, this center point, it will act as center of mass. Why? Because in all the directions, three-dimensional direction, x-axis, along y-axis, along z-axis, all the points, the distribution of mass is same in all the directions. So that is why we have taken this point as center of mass in spherical body. Means you can balance this spherical body over this point. So then take next example. Why we are concentrating so much on the center of mass of the rigid body? Because rigid body, it consists of large number of particles. So to study the motion of the rigid body, we need to study the motion of every particle. It's every particle. That is quite difficult. So that is why we are concentrating that much on the center of mass. Now this is a spherical ball. Suppose it is of spherical body. Suppose it is of 18 kg. And here you have a point mass which is also 18 kg. Same. Suppose they have same mass. 18 kg of spherical body, 18 kg of point mass. And you are dropping both of them and they will be dropped in the same manner. It means to study, instead of studying the motion of this whole spherical body, what you will do? You will just concentrate on this point mass because their behavior is same. Then take the example of the rod which we have already taken. This was the rod and this was the center of mass of the rod, balancing point. Then when you apply force on this rod in this direction, what will happen? You are just applying force on the center of mass of the body. Here note, this force which we are applying this force only on the center of mass of the body. But what you will see, that this whole rod will move in this direction in such a way the particle which is here, it will also experience force in this direction. The particle here will also experience the same F force in this direction. So all the particles, we are applying force on just center of mass of the rod, but it's all of its particles, they are experiencing the same F force in that direction. So all those particles, all these particles, they will move with the same velocity as that of the center of mass. So that is why we will just take and study the center of mass of the rod and not all the points of the rod. So the center of mass of the rigid body, it makes our study easy, because it will be easy to study the motion of the rod by just concentrating on a point mass, that is center of mass, instead of studying the motion of all the particles of the rigid body. And similarly, suppose we have to study the motion of the solid body which is of arbitrary shape. When you will apply force on this rigid body in this direction, what will happen? Every point of this body, it will move in that particular direction with the same velocity. So instead of studying the motion of all the particles of the rigid body, you will just concentrate on this motion of the center of mass. One more thing, that is the center of mass, it does not depend upon the gravitational field. You will be able to understand this after studying center of gravity, because the center of gravity, it depends upon gravitational field. The point of center of gravity, it changes with the change in gravitational field. But this center of mass, it doesn't change with a change in gravitational field. So, next topic is center of gravity. Again, we'll study this definition after doing this. So, again take the example of the same rod whose center of mass is this point. So, we can balance this rod about this point. So, in the second figure, we have balanced the rod about the center of mass. Then, as I have already told you that in case of center of gravity, it depends upon the gravitational field, force due to gravity. Suppose the gravitational field is uniform, means there is equal or uniform force due to gravity here as well as here. So this is equal uniform force due to gravity, and it is attracting this rod towards itself downwards. And what will happen in case of uniform force due to gravity? In case of uniform force due to gravity, neither this rod, it will tilt to this side, and neither it will tilt to downward to this side. It will stay straight. It means in case of a uniform force due to gravity, or in case of a uniform gravitational field, center of mass is same as that of center of gravity. In case of uniform gravitational field, center of mass of the body and center of gravity of the body, they coincide with one another. But in case of a non-uniform gravity, what will happen? On one side there will be more gravitational field, and on the other side there will be less gravitational field. So the side on which the gravitational field is greater, the rod, it will be tilted downward to the side on which the gravitational field is higher. So, but the center of mass will remain same. Why? Because the distribution of mass is equal. Whether it is tilted in this direction, whether it is tilted in this direction, center of mass will remain same, because distribution of mass is same. But because of higher gravitational field on this side, its center of gravity will change than this. Center of gravity of the same rod will change under non-uniform gravitational field. So now we have to find the balancing point such that this rod can be balanced even in the presence of non-uniform gravitational field. So how? From this point, center of gravity will shift here. Center of mass will remain same, but center of gravity has changed. Why? Because on this side G was higher, weight of the rod is same. G is higher means mass on this side it will be smaller. So weight will be same. And on this side, as G is smaller, gravitational field is smaller, so mass should be higher. So that is why mass is higher. Again giving the same value of W. So this is the center of gravity in case of non-uniform gravitational field. So now, what is the definition of center of gravity? It is the point where we are distributing weight. You can see m into g, that is weight. So this is the point where the distribution of weight is equal in all the directions. In this direction weight is W now, and in this direction weight is W now. So center of gravity is the point where the distribution of weight is equal in all the directions, and it depends upon the gravitational field. So in case of non-uniform gravitational field, center of gravity, in case of non-uniform gravitational field, center of gravity and center of mass, they don't coincide with each other. So that is why it is said that center of gravity and center of mass of the body, they may or may not coincide with one another. So this is all in this lecture.